Hey guys, so you may notice this video looks a little bit different because I now have just gotten some new recording equipment for these videos, and so the rest of them should look as nice as this one. I'm really liking the new technology here. So in this video, this is just a clarification on a few things that I've talked about before about phases, and I want to show actually some examples of what happens when you multiply wave functions by phases and what changes, if anything. And so, if just to remind you, a phase is something whose norm squared is 1, and I have here like an example of two phases. And of course, phases, as we also talked about, one of their definitions is they're written in the form e to the I phi or e to the I theta, something like that. Because a complex exponential has a norm of 1. And just a reminder here up here, if you can see where my pointer is, we have two specific examples of phases that are fairly common. You have -1, which is e to the I pi, and I, which is e to the I pi over 2. So that just shows, because they have a norm of 1, and they can be written as a phase like this. And so then I'm going to go back to the superposition, one of the examples that we had, and this is actually an example problem in Griffith's Introduction to Quantum Mechanics, which I've talked about in a few other videos. And so to remind us about some things on the infinite square well, we have up here in the top left corner psi 1, capital Psi 1, which is lowercase psi 1, e to the minus I omega t, or I omega 1 t, where omega 1 is, I have here, omega 1 is pi squared h bar over 2ma squared, right? Because the energy, if you recall from our video before, we got the energy of the first state was pi squared h bar squared over 2ma squared. And because the energy is proportional to n squared, the second energy level is E1 times 2 squared, which is 4, so 4E1, which is 4 h bar omega 1. Which would then be 2 pi squared h bar squared over ma squared. And so we're looking at these wave functions. If we see the capital Psi, where it's lowercase, this one is e to the minus I omega 1t, which makes sense. This one, instead of writing it e to the minus I omega 2t, I'm just writing it in terms of this omega 1, this pi squared h bar over 2ma squared. So we have psi 2 e to the minus 4I omega 1t. Right, because it's 4 times this the angular frequency of the first state. And so now I'm going to take a superposition, and the first one will be simple, and I have my 1 over root 2 as my normalization constant, and we got that a few videos ago. And so if I just add them together, right, the first thing we can see is the probability of getting energy 1 is 1/2, probability of getting energy 2 is 1/2, right? Because if we expand this out, we can see that C1, let's go back to the color that I had here, C1 is 1 over root 2, and C2 is 1 over root 2. Right, and then using that, we can get the expectation value of the energy, which I showed in another video is 1/2 E1 plus E2. Then if we did sine norm squared, which I've done for you, you can show this yourself using properties of exponentials and the relationship between sine and cosine, the relationship from the exponentials to sine and cosine. But well, I've just sort of worked this out on my own, and then you can do the integral with x if you want to, or you can just take my word for it. But for all of these wave functions, I have already found the expectation value position. And so for sine norm squared, the probability distribution, it's got this 1/2 psi 1 squared plus psi 2 squared. What we're really interested in is how the probability density, right, because this is the probability density, how this will change in time. And here we have it oscillates like a cosine, where of cosine 3 omega 1t, which you'll get from the difference between these two. I believe that's the general formula that I showed a few videos ago. And so when we do the expectation value of the position, we have a over 2, which is the middle, which makes sense. The particle will, around the middle of the well, it will oscillate. This is a over 2 here. and around the middle, and then it will oscillate, and oscillate at a frequency of 3 omega 1. And the amplitude of this oscillation is is 16a over 9 pi squared, which ends up being about 0.18a. So if I were actually to show the oscillation, and again, this is the expectation value of x. If I were to actually show the oscillation, it would be probably between these 2 points that the expectation value of x oscillates. And here it oscillates like a cosine wave. So in fact, if we look at the what happens at time equals 0, well, cosine of 0 is 1. It turns out the particle in this case will actually start at time equals 0. It will start on the closer to the left end of the well. So it starts. This one starts near the left end, right? About 0.18 of this distance towards that way. Okay, so now let's look at what happens if I'm not going to multiply this wave function by an overall phase. I'm just going to multiply the second part of the superposition by a phase. So I've got 1 over root 2 times psi 1 minus psi 2 instead of that. Well, now we can look at the probabilities, and it turns out for energy, in terms of energy, these states are actually identical in terms of energy, because if you can see C1, we can see that C1 is 1 over root 2, and C2 is negative 1 over root 2, right? But both have the same norm squared. Therefore, then the expectation value of energy 1/2 E1 plus E2 will be the same. However, when we look at the probability density, we'll get this, 1/2 of psi 1 squared plus psi 2 squared minus 2 psi 1 psi 2 cosine of 3 omega 1t. But notice this is minus over here instead of plus as it was before. So the probability density of these two associated with these two wave functions are not the same. And you can also see in terms of the expectation value of position, instead of minus this cosine term, there's a plus. So actually this particle will start closer to the right. Okay, now let's look at if we take another complex phase. So psi being 1 over root 2, psi 1 plus I psi 2. Again, we can see C1 will be 1 over root 2, C2 will be I over root 2. So probabilities will be the same, energy expectation will be the same. The probability density, though, instead of being a cosine wave, it will actually, instead of oscillating like a cosine, will oscillate as a sine wave. So again, probability density will be different when you have a relative phase here. And then the x, the expectation value of position, well, if we look at time equals 0, this is a sine wave. Look at time equals 0, the expectation value is a over 2. So this particle will start near the middle, or let's do then the gold color here. So we'll start near the middle. And again, these are just the expectation values. There's always probability associated with it, but this will be closer to the middle as opposed to these where it will be favoring one side or the other at time equals 0. Okay, so now that we've looked at this, what happens though if we multiply the wave function by an overall phase, right? Not a relative phase between each of these, component basis wave functions. An overall phase. So if I have I over root 2, right? Well, now C1 is I over root 2 and C2 is I over root 2. Probabilities will be the same. And actually, if you do this calculation, the probability density, if you do this plus, the probability density will be identical to when the normalization constant is just 1 over root 2. So, and same thing with the expectation value of x, that it is actually identical. So it turns out, apparently multiplying the wave function by an overall phase, which I know I've talked about before, actually does end up giving you the same wave function. These two wave functions are physically the same. And now let's look at the general cases, where if I have any general relative phase, e to the I phi, on the second wave function, you can find a general formula for that, and it's right here, where the oscillation does change. So the this relative phase, as you can see in terms of the position and the probability density, actually does have an effect on the wave function. So relative phases do affect the wave function. They don't affect the energy, but they affect other observable quantities like position, and if you did momentum, they would also affect the momentum of the particle. So just because it doesn't have an effect on the energy, it can still have an effect on other properties. And we will see this come up more often, where we have a relative phase will not, like if you're writing it in some basis, it won't have an effect on the probabilities with that one basis, with that observable, but it will affect other observables. Hopefully that makes sense. And so yeah, so it affects x, it affects the probability density. But now if I take this wave function and I multiply it by an overall phase, e to the I theta, it turns out these calculations, and you can see they are exactly the same. So moral of the story here, relative phases, if you have a relative phase between parts of the superposition, it does make a difference. Even though it's not in the energy, it makes a difference in other observable quantities. An overall phase, though, will give you the same exact physical wave function. Okay, I'll see you in the next video.